Okay. Now we will look at concrete examples of our architecture design patterns. First, layers pattern, pipes and filters, repository, model view controller, proxy, and broker. Proxy pattern is actually a detailed design pattern, but to understand broker, I put it here also. These are just a selected set of patterns. There are other patterns, but this gives a nice impression about what architectural pattern is. In the project, you can also use patterns besides of these. So what do we have now? So we said we have client's perspective, requirements analysis. The process that we follow is actually a domain-driven approach. Okay, so what we do is we first look at if we have a problem, we try to identify the stakeholders, their concerns, identify domain, knowledge sources, define the concepts. So it's a domain-driven approach. Based on that, we try to define the conceptual architecture. So it's not directly from requirements, but through a domain-driven approach. The next process is to identify patterns. Once we have the conceptual structure, we look at how can we restructure or enhance the structure using these patterns to improve quality. Excuse me. Okay, and that's actually better. So domain-driven approach complemented with patterns. That's actually the approach that we follow in this course, and that you also should follow, that you are following in the project. So you can use several patterns. The first one is layers pattern. Actually, we have seen this also as a layers view. Why is it view there? Why is it pattern? So it's a pattern because it's a recurring problem to some generic when providing some generic solution. Okay? It's a view in that, from that perspective, because it provides a way how to model the architecture, the system. It says just layer your architecture system. Okay, but in any case, it is also well known as a layering. This is an example of network protocols, where you have communication of various clients over the network. You have different protocols, components at different abstraction levels. Some are low level, others are high level. So formatting of data, bit representation, it's very low level. Error detection, application logic, very high level. Routing, synchronization, dialog control, data transmission. So they are all different at different abstraction levels. So what the layers pattern, so every pattern has a problem that it addresses. A layer pattern addresses this problem. If your large system is characterized with a mix of low and high level issues, okay, where high level operations rely on low level issues, okay, like application logic in the end relies on transformation of the bits, okay, it's very routing, etc. The mapping of high level issues to low level issues is not straightforward. The source code changes should be local and not rippled through the whole system. Portability is required. Modifiability is required. Part of the system must be exchangeable. Several external boundaries of the system are specified a priori. So functional interface and interface must be stable. All these issues taken together, or most of these issues, lead you to the application of patterns. What's the pattern? Layers pattern. It says layer your system in a set of layers. Layer is a subsystem that uses the service of lower layer, lower abstraction, to provide service to higher abstraction. A layer can only depend on lower layers. A layer has no knowledge of higher layers. Okay. This is a solution, so n plus 2, so etc. So typical we have seen also before. This is an example that you might have seen before, for layering of network protocols. This is the standard of International Standard Organization from Open System Interconnection, where you have at the highest level application layer, presentation layer structures information and attaches semantics, session layer defines dialog control and synchronization facilities, transport layer breaks messages into packages and guarantees delivery, network layer selects a route from sender to receiver, data link layer detects and corrects errors, and physical layer transmits the bits. Okay. This was a well-known layering system even before the concept of pattern was introduced, but later on we just say this is a layers pattern, a typical application of a layers pattern. What's the advantage here? So this higher abstraction level, lower abstraction level, portability, we can easily port to a different network layer. The modifiability, we can change easily the transport layer, the implementation, etc. Reuse, okay, standardization, and so on. This is an example of a layers pattern of the TV, digital TV. Here it's like the a sidebar. Okay, all these layers use this infrastructure layer. So you have applications layer, where we have user interface represent the functionality to the user, the middleware layer implementing the user functions, TV platform, the platform actually controlling the hardware, the TV, the hardware, and here you have the infrastructure, operating system support, real-time kernels, etc. Okay. So this is from telecommunications domain, this is from embedded systems domain. So you could have layers pattern in different domains. How do we design these layers? First of all, define the abstraction criterion. Okay, what is based on what are we defining the layers? We determine the number of abstraction levels. How many abstraction levels do we have? We could say we have 4. We name and assign tasks to the layers and specify the service for each layer and define its interface. Okay. Abstraction criteria, define the layers, name the layers and the task, define the interface. Okay. Each layer may itself consist of multiple entities, which we have seen. So layer 3 consists of 3 components. Components in different layers can call each other directly. Alternative is to define an interface, as we have seen also before. Okay, we could define a common interface where all the components can address. What's the dynamics? We could have top-down request, the scenario. A client issues a request to layer N. That's the highest level. Since layer N cannot carry out the request on its own, it goes to the next layer, and so on, till we have the lowest layer, top-down. We could have also bottom-up notifications. We said actually also when discussing the layers as a view, the bottom-up calls are not allowed, but you could have notification. A chain of action starts at layer 1, for example, an exception call, and reports to layer 2, etc., till you get at the client. Okay. Scenario 3, requests travel through subset of layers. It doesn't go through all the layers, but it stops at some layer. Okay. For example, layer n-1 can act as a cache, and the request from level can be satisfied without being sent all the way down to layer 1. Okay. You don't need to travel through all the layers. In a similar sense, the notification can be stopped early on. Event is detected in layer 1 but stops at, for example, layer 3 instead of traveling all the way up to layer n. Maybe the exception is handled there. Okay? This is a similar well-known scenario. You have two stacks of n layers communicating with each other. Well-known scenario from communication protocols. These are the communication protocol stacks. Okay. As we said before, you can relax this. You can have less restrictive, in which each layer may use the service of all layers below it, and not only the next lower layer. But you gain flexibility, but you might lose maintainability. So we should be careful. Known uses of this pattern: network protocol stacks, operating systems, where you have system service, resource managed, kernel, hardware abstraction, and the hardware. Okay. Virtual machines is just layering system. You program, you compile your code, you get the bytecode. Your source code, it goes to platform-specific code, Java version, and you bytecode instructions. It's just layered. API, you have utility functionalities, high-level functionalities, operating system functionalities, information systems, presentation, application, domain layer, database. Okay. So layers actually in different domains. Benefits: reuse of layers. Individual layers with well-defined abstraction could be reused in multiple contexts. Okay. Support for standardization. If you have a clearly defined and commonly accepted interface, you could define a standardization. Dependencies are kept local. Because of standardized interface, the effect of code changes will remain local to the layer that is changed. Exchangeability, individual layer implementation can be replaced by semantically equivalent implementation. Provided that you have the same interface, you can just substitute the implementation. Okay. Drawbacks. It has drawbacks. Cascades of changing behavior. Cross-cutting concerns such as quality of service. Okay. It's just cascaded in each layer. Lower efficiency. You decompose your system into several layers, so communication goes through these layers. So it's not direct call. So it's less. It might be less efficient. And then you could decide not to use a layer. Unnecessary work. Additional or duplicate work throughout the layers. And difficulty of establishing the correct granularity of layers. How many layers should we select? It's not always easy. So we know in the information systems we have the user interface, business logic, and resource layer. But for example, in the digital TVs, what's the correct layering? Okay. So it's not always trivial. So far, layers. Enough about layers. Questions about this? Now let's look at the pipes and filters pattern. That's the second pattern. What's the problem here? You have a system, and the system must process a stream of data. If you have such an application, and typically such systems consist of a sequence of independent processing steps. You get as input a stream of data, and you have some independent processing steps. System has to be built by several developers, and requirements are likely to change. That means the processing steps might be exchanged or reordered. Future requirements must be possible by exchanging or reordering processing steps. So a stream of data, it must be processed by some components, and the ordering can change. If you have such a kind of application, you might think of applying a pipes and filters pattern. The pipes and filters pattern consists of 4 components. A filter component, which processes the units of pipeline, which processes the data. It's processing units of the pipeline. So it gets, I don't know whether you can see it. It gets the input data. It performs some actions on the data and provides to the output. Okay, that's filter. Filter, you get data, processing, output. The pipes denote the connections. They just connect the filters. What the key role is just transferring the data, buffering data, synchronizing filters. Okay. You have a data source, represents the input to the system, actually the first filter, we could say. For example, not the first filter, but for example, the file consisting of lines of text or sensor delivering sequence of numbers. Okay, the data source, where does the data come from? And the data sink is the eventual, the node collects the results from the end of the pipeline. Okay? So typically then, the solution could be like this. So you structure your system as a pipeline consisting of filters, okay, and pipes which connect these filters. You have a data source in the beginning and data sink. And every filter is independent from other filters. There's no shared data among these filters and no knowledge about other filters. Okay. The only thing what each filter does is its own responsibility. What's that? Get the data, transform data, put to the output. Okay. What's the responsibility of the pipes? Like here, connecting these filters. Okay. Typical example of a pipes and filters pattern, application of a pattern, is the compiler's application, compiler architecture. Traditionally, these compiler architectures were indeed structured in this way. So you get some program, source program, and the compiler maps that program text into programming language code. Oops. This is very difficult to do in one step. You have lots of streams, so what in the compilation domain, what they do is they define individual steps, individual processing units. For example, you have the scanner, which looks at the tokens, the parser, semantic analyzer, code generator, and executable code. So we could say this is the data source, this is the data sink. These are the processing units, that is the filters, and these are the nodes. Okay? So if you have ever developed a compiler, typically this was the architecture. If we look at the TV, digital TV, the top level decomposition of that was a layered architecture. Now we see also how we combine these patterns. It appears that the lowest layer, the TV platform software, is a pipes and filter structure. Okay? Because there we get the signals, TV signals, audio video signals, and these signals should be processed by the tuner, the demodulator, analog digital converter, You get digital. If you get digital I/O, you get processed the audio processor, video processor. They are all different filters. Okay, each of these is independent of the other filter. What it only does is it gets the input, it processes the input, it puts to the output. Okay, so top level decomposition is layers, and if we just look at the TV platform software layer, it appears that it is like pipes and filter structure. Here we could have other patterns. Here also, but this is just one example. If you look at the dynamics of this pattern, the pipes and filters, there are different dynamics. So we have data source, some filters, and data sink. Scenario 1. Scenario 1 shows a push pipeline, it's called like that, in which the activity starts with the data source. The data source just pushes data to the first filter. So this is push, push, push. This processes the data and push to the next filter. Process data, push to the next filter. Eventually to the data sink. Okay? You could have also pull pipeline. Your data source is not active, it's passive. It's just data source, it's just repository, but some filter pulls the data from the data source. Okay? The control flow is started by the data sink calling for data. So it doesn't start here, but actually here we see it starts even here by the data sink. It reads, provides a read request to the filter. Then this filter pulls from this filter, read request here, eventually read request to the data source. Okay, so there's a push pipeline, the data is pushed, and a pull. We ask for data. Okay, see, this is a same pattern, but different application. You might need to reconsider which alternative is suitable for your application. Okay? So you have to explicitly describe that. You could have also, of course, a push-pull pipeline, where filter 1 here is a pull, filter 2 is both a pull and push. This scenario 3 is a mixed push-pull pipeline with passive data source. Passive means it doesn't do anything from itself, it's not proactive, it's there, and somebody has just to get the data. Here's the passive data source, and data sink is also passive here. Filter 1 is pull, it pulls the data from the data source, which is actually started from the filter 2. So it reads request from filter 2 to filter 1. Filter 1 gets the data, okay, and then it's provided to the filter 2. Eventually it's written to data sink. Okay. So in this case, you have two databases actually, or two data sources could be. Both are passive. This is even a more complex but typical behavior of pipes and filter system. All filters actively pull, compute and push data in a loop. So they can just pull and push the data. As such, each filter runs in its own thread of control, for example in separate process. So it's not just sequential. They are all active. Could be like agents. Okay, these filters could be like agents. They are self-autonomous. The filters are synchronized by a buffering pipe between them. Here, for the synchronization, because they can just call at any time. Push-pull. You put here a buffering pipe which synchronizes. So architectural design decision. And this scenario shows also parallel execution using filters. The others were more sequential, but this is more complicated. Okay. How do you design this? You divide your system's task into a sequence of processing steps. Okay, what are the processing steps? What is the data source? What is the data sink? What are the processing steps? You define a data format to be passed along each pipe. You put, you put something to the output of the filter, which should be put on the pipe. Okay, and the pipe accepts some data format. You define that. You decide how to implement each pipe connection. Design and implement the filters and set up the processing pipeline, which might not be trivial. There are different variations. Pipelines are just linear sequences of filters. There's no branches. Bounded pipes is another variation, where you say you have the pipe between the filters. You say every pipe has some bandwidth, so the amount of data on each pipe is restricted. Okay. Which is actually in practice the case. Type pipes, okay, where you have pipes which only allow data of a specific type. Batch sequential system is a specific case where each step runs to completion before the next step starts. So this is the counterpart of the parallel pipes. You put on the pipe, on the filter, the next filter can just start if the current filter has processed the data and put to the output. Okay, the batch sequential. So again, it's one pattern but multiple variations. What are the benefits? Understandability. The overall input-output behavior is clear. No complex component interactions. You have split actually the overall processing step into several processing units. So it's understandable. Like in the compilers, you have just scanning, parsing, code generation. They are all different steps. Reuse, maintainability, and extensibility. Filters are actually black boxes. They don't know about other filters. They have just like black box. They have some input, output, and we could easily reuse these and maintain and extend. This enables certain kinds of specialized analysis, for example, throughput analysis. Okay, by looking at these filter architectures. What are the drawbacks? You have the batch mentality. You have the pipes. They should be processed. And here the assumption is there's actually no interaction. So if you have an interactive system, this is not the pattern that you should use. Okay, because this is like just you have some processor, you put just data, the system just processes, and you get at the data sink. If you have a very highly interactive system, don't use this pattern. It's hard to maintain correspondences among filters. Because they are independent, that's the benefit, but it's also hard to maintain this correspondence. Filter ordering can be difficult. What should be put first? What next? Filters cannot interact cooperatively to solve a problem. So if you have a problem in which different components need to cooperate, then this is also not the right pattern. This is just for transform some data, right? If you need interaction, cooperation, this is not the right pattern. Loss of performance due to a lowest common denominator on data transmission. So it's like a filter chain, right? Okay, the strength of the chain is defined by the weakest chain, right? The chain element. So if you have a very weak filter where the performance goes down, it will just impact the complete system. Okay. What are the examples here? Unix shell, batch systems, compilers, language processors, etc. So any application where you have a bunch of data, stream of data, where you can identify processing units. Then you should structure your system as a pipes and filters approach. Clear? Questions? Okay, then I explain this one too. Blackboard pattern. It's the last pattern, and then we wrap up. What's the problem here? In the pipes and filters pattern, we didn't have cooperation. We didn't have cooperative problem solving. If you have that, you could think about Blackboard pattern. This is typically for problem solving in immature domains, where you don't have a feasible deterministic solution. The problem decomposition results in sub-problems that require different fields of expertise. The solution to partial problems require different representations and paradigms. You don't have a deterministic strategy how partial problem solvers should combine their knowledge and might require experimentation. Problem solving, immature, we want to requires multiple domain experts, but we would like to actually experiment. Okay. Example from medical diagnosis. If a patient gets ill, he or she gets a patient document, goes to the main doctor, provides the patient document, then he might consult, he or she, different domain experts. Okay? And different domain experts will write on the same patient document. Okay, the nurse for checking the blood pressure, whatever, some lab analysis, and they all write on the same patient document. In the end, we hope that you get some diagnosis. Okay? You say, hey, after all this investigation, this is the diagnosis. Okay? You have the flu. Okay, like me had. And then based on that you get the therapy. Okay? But the idea here is common cooperative problem solving. But you are not sure yet about the solution. What's the Blackboard? This is the Blackboard here actually. What are the experts? These are domain experts. This is coordinator. So this is typically a Blackboard pattern. Blackboard solution. You have one Blackboard which stores and manages central data. Okay. You have some knowledge sources. They are independent components that contain some domain-specific knowledge. They are some experts. Solve specific aspects of the problem and updates the Blackboard. And you have one control system which coordinates. So who is going to write when on the Blackboard? Okay, coordination. This is the pattern, quite simple, right? Blackboard, knowledge source, control system. The relations, you have data flow plus control flow. The control is just coordination. Data flow, they write to the Blackboard. Okay, it's easy. Blackboard design, how do you do that? You define the problem, the domain, and general fields of knowledge necessary to find the solution. To solve this problem, what kind of knowledge source do I need? Knowledge experts. Divide the solution process into steps. Divide the knowledge into specialized knowledge source with certain subtasks. Define the vocabulary of the Blackboard. So everybody will write, but that should be with the common language. Specify the control of the system, the knowledge source, what's the prioritization, can anybody write at any time, or do we apply some prioritization? Implement the knowledge sources. This is the variant that you know actually of the Blackboard. You have just repository. You don't have control, like here, you don't have this. Then you have just repository knowledge sources. Then you have shared data. These are the clients. They just write to the shared data. The knowledge source evaluates its own applicability, computes the result, and updates repository. Okay, that's the Blackboard variant. Benefits of Blackboard: experimentation. You can just experiment with the knowledge, so they just write on the Blackboard. Changeability and maintainability. Blackboard control and knowledge source are strictly separated. You can easily change and maintain these. Reusable knowledge sources. Okay, they should understand the protocol of Blackboard to get integrated into the system. Support for fault tolerance. Noisy data and uncertain conclusions are allowed, like that in the medical diagnosis. They can just write anything on the patient document. All results are hypotheses, but in the end these hypotheses are put together and a conclusion is drawn. Support for robustness. In due time, only strongly supported hypotheses will survive. Drawbacks: difficulty of testing. Results are often not reproducible. It's no good solutions guaranteed. You have different domain experts, but all the things that are written is hypothesis. Difficult to establish a good control strategy. You might need experimental approach. So who is going to write when? High development efforts. It might take years to evolve and stabilize. Okay, you have a huge Blackboard, different knowledge source, different experts throughout the world. So it's not easy. There's no support for parallelism. Concurrent access to central data must be synchronized. Or you should define another pattern with this Blackboard to solve this concurrency problem. Example: speech recognition systems, pattern recognition, signal processing, loosely coupled agents, batch sequential systems, pipeline architecture with shared information. They are all examples of Blackboards. So this is the last pattern that we discussed today. You might already have some ideas about using some of these patterns in the project, in your project. Layered pattern is not the only solution. There are also other solutions. Even if you use the layered, as we have seen, there are different alternatives. Okay, and you have to describe that explicitly. We will continue next time with the other patterns, selected patterns. For now, do you have any questions? Okay. I'll see you next time. Thanks.